When Richard Feynman spoke about gravity, he often began by dismantling the most comfortable idea people hold, that gravity is a mysterious pulling force that somehow reaches across empty space and drags objects together. This picture is simple, memorable, and useful for everyday calculations, but Feynman believed it hides the deeper truth. The real problem, he argued, is not that gravity is difficult, but that we mistake familiarity for understanding. We have lived with gravity since birth. We feel it in our muscles, see it in falling objects, and build our intuition around it. That intimacy makes us think we know what gravity is, even when we do not. To understand what Feynman meant, it helps to begin with what we usually call a force. A force, in ordinary experience, comes from interaction. A push involves contact. A pull involves tension. Even forces like friction or air resistance depend on matter colliding with matter. Gravity stands apart. Two objects attract one another even when nothing visible connects them. There is no thread, no fluid, no mechanical linkage. Calling this attraction a force is already a compromise between reality and language. It allows us to calculate motions, but it does not tell us what gravity actually is. Feynman was deeply uncomfortable with explanations that merely rename a phenomenon. He famously criticized answers that replace mystery with vocabulary. Saying that objects fall because of gravity is, in his view, not an explanation at all. It is equivalent to saying that opium causes sleep because it has a dormitive virtue. The label gives the illusion of understanding without providing any mechanism. Gravity, when treated as a force, becomes one of these labels. We feel satisfied, but we have not learned what is truly happening. The confusion grows stronger because gravity behaves differently from other forces. Electromagnetism, for example, can attract or repel. Gravity only attracts. Electric forces can be screened or neutralized. Gravity cannot. Electric charges come in positive and negative forms. Mass does not. These differences suggest that gravity is not simply another force alongside the others. Feynman emphasized that whenever nature behaves in a fundamentally different way, it is usually a sign that our conceptual framework is incomplete. This realization led physicists, including Einstein, to a radical shift. Instead of asking how objects pull on one another, Einstein asked how objects move when no force is acting at all. In classical physics, motion without force means moving in a straight line at constant speed. But what does straight really mean? On a flat surface, straight lines are obvious. In curved spaces, they are not. A plane flying from one city to another follows a curved path on a map, yet it is flying as straight as possible on the curved surface of Earth. Feynman loved this analogy because it exposes how deeply geometry influences motion. The plane is not being pulled sideways by some mysterious force that bends its path across the globe. It is simply following the most natural route available on a curved surface. From this perspective, motion that looks forced may actually be free motion misunderstood. Gravity, in this view, is not a force acting on objects, but a feature of the environment through which they move. Massive objects change the structure of spacetime itself, altering what counts as a straight path. When an apple falls from a tree, it is not being yanked downward by an invisible hand. It is following the straightest possible route in a spacetime that has been distorted by Earth's mass. To us, standing inside that distorted spacetime, the motion looks like acceleration. Feynman emphasized that this idea is not philosophical poetry, but a precise physical statement. The equations of general relativity describe exactly how mass and energy shape spacetime and how spacetime tells matter how to move. The elegance of this framework lies in its economy. There is no extra force law for gravity. Objects simply move according to geometry. Gravity disappears as a force and reappears as structure. This leads to one of the most counterintuitive consequences, which Feynman found both amusing and profound. A freely falling object is not accelerating in the deepest sense. It is doing exactly what it would do if gravity were absent. It is following its natural path. The object that is truly accelerating is the one prevented from falling, such as a person standing on the ground. The ground pushes upward, forcing the person away from their natural trajectory. What we experience as weight is not gravity pulling us down, but the resistance of the earth pushing us up. This reversal of intuition is difficult to accept because our senses are trained by experience, not by geometry. We feel pressure in our feet and assume gravity is pressing us downward. In reality, according to this view, gravity is absent in free fall. Astronauts orbiting Earth feel weightless not because gravity is weak, but because they are falling freely around the planet. Feynman delighted in this point because it reveals how misleading direct sensation can be. Another source of misunderstanding comes from imagining gravity as something that acts instantaneously across space. In Newton's formulation, gravity seemed to operate without delay. If the sun moved, Earth would somehow know immediately. Even Newton was uncomfortable with this idea. Feynman pointed out that Einstein resolved this discomfort by showing that changes in gravity propagate at a finite speed, the speed of light. This again suggests that gravity is not a simple pull, but a dynamic property of spacetime that evolves and transmits information. When massive objects accelerate, they disturb spacetime in a way that produces ripples, now known as gravitational waves. These waves are not forces traveling through space. They are changes in the geometry of space and time themselves. Detectors on Earth measure these tiny distortions, confirming that gravity behaves less like a force and more like a fabric that can stretch and vibrate. Feynman often warned against trying to visualize these ideas too literally. Spacetime is not a rubber sheet floating in a higher, dimensional space. That picture is a teaching tool, not reality. The true description is mathematical, and our brains resist it because we evolved to deal with solid objects, not four-dimensional geometry. Yet refusing to accept the mathematics does not make the universe simpler. It only makes our understanding poorer. What people get wrong, Feynman argued, is believing that gravity should make intuitive sense. They expect a story involving pushes and pulls because that is how everyday interactions work. But nature is not obligated to conform to human intuition. Gravity is subtle because it arises from the deepest level at which space, time, and motion intersect. Any attempt to reduce it to a simple mechanical picture inevitably distorts it. This misunderstanding also affects how people think about explanation itself. Many assume that explaining gravity means identifying a cause in the traditional sense, something that produces gravity the way fire produces heat. Feynman challenged this expectation. At some point, physics reaches a level where explanation means description of patterns, not identification of causes in familiar terms. Gravity is one of those cases. We can say how spacetime behaves, how objects move, and how predictions match observation, but asking why, in the everyday sense, may not have an answer. Feynman was not dismissive of curiosity. On the contrary, he believed curiosity thrives when we recognize the limits of our understanding. He often said that it is more interesting to live with questions than with false certainty. Gravity, as he saw it, is a perfect example. The more deeply we study it, the stranger it becomes, yet the more coherent our descriptions grow. This perspective reshapes how we think about scientific knowledge. Instead of seeing science as a collection of facts that explain everything, Feynman saw it as a method for refining our descriptions of nature. Gravity is not a thing we possess or a force we hold in our hands. It is a pattern in how matter and motion behave. Our theories capture that pattern with increasing accuracy, even if they never satisfy our desire for simple stories. In everyday life, we will continue to say that gravity pulls things down. That language is practical and harmless when used with awareness. The danger arises when we mistake that shorthand for truth. Feynman's message was not that people are stupid for using simple ideas, but that they should remain aware of their limitations. Gravity is not wrong when described as a force. It is incomplete. Ultimately, what Feynman wanted people to understand is that gravity reveals something profound about the universe. Reality is not built from forces acting in space, but from relationships embedded in space and time themselves. Motion, mass, and geometry are inseparable. Gravity is the name we give to this relationship, not the cause behind it. When we let go of the need for gravity to behave like a familiar force, we gain something richer. We gain a universe where falling is freedom, weight is resistance, and space itself participates in the dance of matter. That shift in perspective does not make gravity easier, but it makes it more honest. And for Feynman, honesty about what we do not know was always the first step toward real understanding. Richard Feynman often said that the greatest obstacle to understanding gravity is not mathematics, but habit. We are used to standing still on the ground and calling that state at rest. Everything else falling, moving, accelerating, feels like motion imposed by some external cause. Yet this assumption quietly reverses the truth. To see where people go wrong, Feynman liked to shift the frame of reference, because gravity reveals its true nature only when we stop assuming that the ground beneath our feet is a privileged position in the universe. Imagine floating freely in deep space, far from stars, planets, and galaxies. There is no up or down, no weight, no sense of direction. If you release an object, it remains beside you, drifting calmly. Now imagine that this peaceful state is interrupted as the entire space you occupy begins to accelerate. Without warning, the floor beneath you pushes upward, your body feels heavy, and the object you released falls to the floor. From inside this system, everything behaves exactly as it does on Earth. The object accelerates downward. You feel weight, time, motion, and cause all appear normal. Feynman emphasized that this is not a thought experiment meant to confuse, but a clue meant to clarify. If acceleration can perfectly mimic gravity, then gravity may not be a force in the usual sense at all. It may be something that emerges from how motion is observed. The critical mistake people make is assuming that acceleration and gravity are fundamentally different phenomena. In reality, they are locally indistinguishable. This idea, known as the equivalence between gravity and acceleration, is deceptively simple. Yet it dismantles centuries of intuition. If you are inside a closed box, there is no experiment you can perform to tell whether the force pressing you against the floor comes from gravity or from acceleration. Light bends the same way, objects fall the same way, clocks behave the same way. This equivalence is not approximate. It is exact. Feynman loved this result because it strips gravity of its mysticism. Gravity does not need a special explanation if it can be replaced by acceleration. Instead, we must explain why acceleration feels the way it does. The sensation of weight is not evidence of gravity acting on you. It is evidence that something is preventing you from following your natural motion. In everyday life, we say a falling object accelerates because gravity pulls it downward. But from the perspective Feynman encouraged, this description is backwards. The falling object is not accelerating in the deep physical sense. It is doing what it would do if nothing acted on it at all. It is the object that resists falling. The ground, the floor, the chair. That is accelerating the object upward. This inversion of perspective is uncomfortable because it challenges the reliability of our senses. We feel pressure in our muscles and bones and conclude that gravity is pushing down on us. In truth, that pressure comes from the ground pushing up. Gravity, in free fall, disappears completely. Astronauts orbiting Earth are not beyond gravity's reach. They are immersed in it. They feel weightless because they are allowed to fall freely. Feynman often pointed out that the word free in free fall is not poetic. It is literal. Free fall is motion without force. This idea contradicts everything we are taught as children, yet it is central to modern physics. The experience of gravity arises only when free fall is interrupted. Reference frames play a crucial role in understanding this. A reference frame is simply a perspective from which motion is measured. From the ground, a falling apple accelerates downward. From the apple's own frame, it is at rest while the earth rushes upward. Neither description is more correct than the other. What matters is consistency within the chosen frame. People tend to believe that one frame must be the real one. Feynman rejected this instinct. Physics, he argued, does not care about human preferences. It cares about relationships that remain consistent across frames. Gravity becomes confusing only when we insist on privileging the ground as the natural state of rest. Once we let go of that privilege, gravity begins to resemble a coordinate effect rather than a force. In an accelerating frame, fictitious forces appear. A car that suddenly speeds up makes passengers feel pushed backward. No mysterious force pulls them. Their bodies simply resist the change in motion. Gravity behaves the same way. It emerges when we describe motion from a non-inertial frame, such as the surface of a planet. Feynman enjoyed highlighting that this does not make gravity unreal. It makes it subtle. A fictitious force is not imaginary in its consequences. The discomfort in your body is real. The falling objects are real. What is fictitious is the idea that there must be a physical agent pulling on everything. This insight explains why gravity affects all objects equally. Heavy objects and light objects fall at the same rate not because gravity is polite, but because free motion is universal. Acceleration due to gravity does not depend on mass because it is not caused by a force acting on mass. It is caused by the geometry of motion itself. Feynman found this deeply satisfying because it replaces arbitrary rules with necessity. There is no special tuning required for gravity to affect all objects the same way. That equality emerges naturally once gravity is understood as an aspect of acceleration and reference frames. Light provides an especially striking example. Light has no mass, yet it bends in a gravitational field. If gravity were a force pulling on mass, this would make no sense. But if gravity is equivalent to acceleration, then light must bend, because acceleration affects all motion, not just massive objects. An accelerating frame causes light paths to curve. Gravity does the same. This realization shocked early physicists because it violated deeply held assumptions. Feynman enjoyed reminding people that shock is a sign of learning. Whenever reality conflicts with intuition, intuition must yield. Reference frames also explain why gravity can be transformed away locally. In a small enough region of spacetime, gravity can be eliminated by choosing a freely falling frame. Inside such a frame, the laws of physics reduce to those of special relativity. Gravity vanishes. This is not an approximation. It is exact in the limit of small regions. This ability to remove gravity by changing frames demonstrates that gravity is not an intrinsic force like electromagnetism. You cannot transform away electric forces by changing frames. Gravity alone has this special property. Feynman saw this as a clue that gravity belongs to a different category entirely. The deeper implication is that gravity is not something happening within spacetime. It is something about spacetime. Acceleration changes how spacetime is sliced into space and time for an observer. Gravity does the same. They are two faces of the same phenomenon. People often resist this idea because it seems to undermine the solidity of reality. If gravity depends on reference frames, does that mean it is subjective? Feynman was careful to emphasize that this is a misunderstanding. The experiences depend on frames, but the underlying structure does not. Physics describes relationships that remain true regardless of how they are described. The mistake is confusing description with existence. Gravity does not vanish when you change frames. It vanishes from the equations because the frame absorbs it. The physical predictions remain the same. Objects collide, orbits persist, clocks tick differently, reality remains stubbornly consistent. Feynman liked to compare this to describing motion on Earth. From the ground, the sun appears to move across the sky. From space, Earth rotates. The motion of the sun is not an illusion. It is a valid description from a particular frame. Insisting that only one description is real misses the point. Gravity, viewed through this lens, becomes less mysterious and more profound. It is not an extra ingredient added to the universe. It is woven into how observers measure motion. The universe does not need a force to tell objects how to fall. It only needs consistent rules for how motion is observed. This realization also changes how we think about explanation. Asking what causes gravity becomes less meaningful. Gravity is not caused, it is encoded. It is a consequence of how reference frames relate to one another in a universe where spacetime is dynamic. Feynman believed that accepting this requires intellectual humility. We must give up the demand that nature behave according to our mental pictures. Acceleration and gravity feel different to us because we experience them differently, not because they are fundamentally different. When people insist on imagining gravity as a pulling force, they are clinging to a metaphor that has outlived its usefulness. That metaphor works for throwing balls and building bridges. It fails when we ask deeper questions. Feynman's goal was never to take away useful tools, but to prevent those tools from becoming obstacles. In the end, what everyone gets wrong about gravity, according to this viewpoint, is thinking it acts on objects. Gravity acts on perspectives. It shapes how motion appears depending on how you move. Acceleration reveals this truth by stripping away the illusion of a preferred state of rest. Once this is understood, gravity stops being strange and starts being inevitable. Any universe that allows consistent motion and acceleration must exhibit something like gravity. It is not a special force added to the laws of physics. It is the price paid for living in a universe where motion is relative and spacetime responds to energy. Feynman found this both unsettling and beautiful. Unsettling because it denies us simple causes. Beautiful because it reveals a deeper unity beneath everyday experience. Gravity and acceleration are not separate stories. They are the same story told from different points of view. When Richard Feynman talked about Einstein and gravity, he was careful to remove the aura of mystery that often surrounds both. Many people believe Einstein replaced Newton's simple gravity with something mystical or abstract, as if space suddenly became magical. Feynman strongly disagreed with this impression. In his view, Einstein did not make gravity stranger. He made it more honest. The real revolution was not about inventing a new force, but about redefining what motion, space, and time actually mean. Before Einstein, physics was built on a quiet assumption that almost no one questioned. Space was thought to be a rigid, unchanging stage. Time flowed at the same rate everywhere. Objects moved through this fixed background, and forces acted upon them to change their motion. Gravity, in this picture, was one of those forces. It reached across space and pulled masses toward one another. The mathematics worked, the predictions were accurate, and everyday experience supported the idea. There seemed to be no reason to doubt it. Feynman emphasized that the danger of such success is complacency. When a theory works well, people stop asking what its assumptions really mean. Newton himself was uneasy about gravity acting at a distance, but later generations accepted it without complaint. Space and time became invisible scaffolding, never questioned, never examined. Einstein's genius was to notice that this scaffolding was not neutral. It was shaping the way physicists thought, and it was quietly limiting what they could understand. Einstein began not with gravity, but with motion. He asked how motion should be described if the laws of physics are the same for everyone, regardless of how they move. This simple demand shattered the idea of absolute space and absolute time. If motion is relative, then measurements of distance and duration must also depend on the observer. Space and time could no longer be separate, rigid entities. They became intertwined, flexible, and dependent on motion. Feynman liked to point out that this shift alone was already radical. Once space and time lose their absolute status, the idea of gravity as a force acting within them becomes questionable. If the stage itself is flexible, then perhaps what we call forces are really features of the stage. Einstein's next step was to take seriously the equivalence between gravity and acceleration. If acceleration can mimic gravity perfectly, then gravity cannot be something extra added on top of motion. It must be built into the description of motion itself. This realization forced Einstein to abandon the idea that straight lines and uniform motion are defined once and for all. Instead, they depend on the geometry of spacetime. In everyday life, we think we know what a straight line is. It is the shortest path between 2 points, but this definition quietly assumes a flat space. On a curved surface, the shortest path may look curved to an outside observer. Feynman often used this analogy because it reveals how deeply geometry affects intuition. Motion that appears curved may actually be the straightest possible motion in a curved space. Einstein applied this idea to the universe itself. Massive objects distort spacetime, changing what counts as a straight path. Objects moving through this distorted spacetime follow paths that appear curved when viewed from a flat perspective. This curvature is what we perceive as gravity. Feynman stressed that this is not a metaphor. It is not a story invented to make equations sound poetic. The equations of general relativity precisely describe how spacetime curves and how objects move within it. Gravity is not an added force. It is the geometry of motion. This explains why Einstein did not simply modify Newton's law. He replaced the entire framework. Newton described how forces cause acceleration in a fixed space and time. Einstein described how spacetime itself determines motion. Once this shift is made, gravity ceases to be a force in the traditional sense. People often misunderstand this and imagine spacetime as a physical substance, like rubber being stretched. Feynman warned against taking such images too seriously. Spacetime is not a material object. It does not exist inside something else. It is the structure of relationships between events. Curvature is not bending into a higher dimension. It is a change in how distances and times relate to one another. This abstraction makes many people uncomfortable. They want something tangible, something they can picture. Feynman understood this desire, but he insisted that nature does not adjust itself to human imagination. The mathematics is not a translation of a picture. The picture is a rough hint at what the mathematics says. Einstein's redefinition of motion also explains why gravity treats all objects equally. In Newton's framework, this equality is mysterious. Why should a feather and a stone fall at the same rate? In Einstein's framework, the question disappears. All objects follow the same geometric paths through spacetime. Their mass does not determine how spacetime guides them. Mass determines how spacetime is shaped, not how objects move within it. Feynman loved this economy. One principle replaces many rules. There is no need to postulate a special gravitational force that somehow knows how heavy an object is. Geometry does the work automatically. Another consequence of Einstein's approach is that gravity affects time itself. Clocks tick at different rates depending on their position in a gravitational field. This is not because gravity reaches into clocks and interferes with their mechanisms. It is because time is part of spacetime. If spacetime is curved, then time flows differently in different regions. Feynman emphasized that this is not philosophical speculation. It has been measured and confirmed. Clocks on satellites run at different rates than clocks on Earth. If these effects were ignored, modern navigation systems would fail. Gravity, in Einstein's sense, reshapes time as much as space. This idea deeply unsettles people because time feels sacred. We experience it as a steady flow, independent of location or motion. Einstein showed that this experience is local, not universal. Feynman saw this as another example of how human intuition, shaped by limited experience, resists broader truths. Einstein did not invent complexity for its own sake. He followed logic where it led. Once space and time were no longer absolute, gravity could no longer be a simple force. The universe demanded a new description. Feynman often remarked that the brilliance of Einstein's theory lies in its inevitability. Once the assumptions are accepted, the conclusions follow. Gravity as curvature is not a creative flourish. It is the only consistent way to combine relativity, motion, and observation. People sometimes ask whether Einstein explained what gravity really is. Feynman would say that Einstein explained how gravity behaves, not why it exists in a metaphysical sense. Physics does not answer every kind of why. It answers how relationships work. Demanding more may reflect a misunderstanding of what explanation means. Einstein replaced a force with geometry, but he did not eliminate mystery. He relocated it. Instead of asking why masses pull on each other, we ask why spacetime responds to mass and energy. The mystery remains, but it is a more precise mystery. Feynman believed this precision matters. Vague mysteries breed confusion. Precise mysteries guide research. Einstein's theory tells us exactly where our understanding ends and where new questions begin. One of the most profound consequences of this redefinition is that gravity becomes inseparable from the structure of the universe. There is no gravity switch that can be turned off. Even in empty space, spacetime exists, ready to respond to energy and motion. Gravity is not something added later. It is present wherever spacetime exists. This perspective also changes how we think about prediction. In Newtonian gravity, one calculates forces and then determines motion. In Einstein's gravity, one calculates spacetime geometry and then reads motion from it. Objects do not need to be told how to move. They simply follow the paths available. Feynman admired this because it removes unnecessary instructions from nature. The universe does not compute forces step by step. It simply is what it is, and motion emerges. Many people resist Einstein's ideas because they feel removed from everyday experience. Feynman argued that this resistance is misplaced. Everyday experience is not a reliable guide to fundamental truth. It is shaped by survival, not by accuracy at extreme scales. Einstein's theory succeeds precisely where intuition fails. It explains the orbit of Mercury, the bending of light, the slowing of time, and the existence of gravitational waves. Each success reinforces the idea that redefining motion and space was not an aesthetic choice, but a necessity. Feynman also cautioned against hero worship. Einstein did not possess mystical insight. He followed questions to their logical conclusions and refused to ignore inconsistencies. Anyone could, in principle, do the same. The difficulty lies not in intelligence, but in letting go of comfortable assumptions. In this sense, Einstein's contribution is a lesson as much as a theory. It teaches us that understanding sometimes requires abandoning deeply held ideas, even when they feel obvious. Space and time feel fixed because we live at low speeds and weak gravitational fields. Step outside those conditions, and their flexibility becomes unavoidable. What people get wrong, Feynman believed, is thinking Einstein complicated gravity. In truth, Einstein simplified it by revealing its true nature. Gravity is not an actor performing within spacetime. It is the script itself. Once this is understood, gravity becomes less like a mysterious pull and more like a rule governing motion. Objects move the way they do because spacetime is the way it is. There is no deeper mechanism hidden behind the scenes. This realization does not diminish wonder, it deepens it. The idea that space and time themselves participate in the dynamics of the universe is far more astonishing than an invisible force tugging at objects. Einstein did not destroy common sense. He showed its limits. Feynman wanted people to appreciate this shift without mystifying it. Einstein did not turn gravity into magic. He turned it into geometry. The magic disappears when we stop demanding that reality resemble our instincts. In the end, Einstein redefined motion and space not to confuse us, but to make gravity intelligible. What feels strange is not the universe, but our expectations. Gravity is not what we thought it was because space and time are not what we thought they were. And once that is accepted, gravity stops being a puzzle of forces and becomes a story about structure, consistency, and motion written into the fabric of reality itself. Richard Feynman often emphasized that one of the most stubborn misunderstandings about gravity comes from how we think about falling. From childhood, we are taught that falling means being pulled downward by Earth. This idea feels so natural that questioning it seems pointless. Yet Feynman argued that this assumption hides one of the most radical truths in modern physics. Objects that are falling are not being acted upon by gravity in the way we imagine. They are doing precisely what they would do if gravity did not exist at all. To appreciate this, Feynman encouraged people to reconsider what it means for an object to move naturally. In classical thinking, natural motion is rest or uniform straight line motion. Any deviation from this requires a force. Falling, therefore, must require a force called gravity. But this framework quietly assumes a fixed background of space and time. Once that assumption is removed, the meaning of natural motion changes. In Einstein's view, natural motion is motion along the straightest possible paths in spacetime, known as geodesics. These paths are not defined by our intuition, but by the geometry of spacetime itself. An object following such a path is not being pushed, pulled, or forced. It is simply moving freely. When an apple detaches from a tree, nothing suddenly grabs it. No new interaction begins. The apple was previously prevented from moving freely by the stem of the tree. When that constraint is removed, the apple begins to follow its natural path through spacetime. To us, standing on the ground, that path looks like acceleration downward. To the apple, there is no force at all. Feynman loved this reversal because it exposes how deeply language misleads us. We say the apple falls because gravity acts on it, when in fact the apple falls because nothing acts on it. The true force appears when the apple hits the ground. At that moment, it stops following its natural path and is violently forced away from it. This perspective also explains why astronauts experience weightlessness. Orbiting Earth, they are constantly falling. Their sideways motion ensures that they keep missing the planet, but they are always in free fall. Gravity has not vanished. It is present everywhere around them. What has vanished is resistance. Feynman often highlighted how difficult it is for people to accept that weight is not a measure of gravity acting on them, but a measure of how strongly they are being prevented from falling. Standing on a scale, the reading reflects the upward force exerted by the scale on your body. In free fall, the scale reads 0, not because gravity disappears, but because nothing pushes back. This insight turns common sense upside down. We are accustomed to thinking that falling is an active process, and standing still is passive. In reality, falling is passive, and standing still requires continuous force. The Earth must push on you every moment to keep you from following your natural trajectory. Feynman saw this as a profound lesson about the danger of trusting sensations. We feel heavy when standing and light when falling. Our minds conclude that gravity increases when standing and decreases when falling. The truth is the opposite. The sensation of weight arises from contact forces, not from gravity itself. This understanding also clarifies why all objects fall the same way. In free fall, mass plays no role. The path is determined solely by spacetime geometry. A hammer and a feather fall differently in air because of air resistance, not because gravity treats them differently. Remove the air, and the difference vanishes. Feynman enjoyed pointing out that this equality is not a coincidence. It is a necessary consequence of free motion. If gravity were a force acting on mass, there would be no obvious reason for different masses to behave identically. The universality of free fall would be a mystery. In the geometric view, it is inevitable. Another source of confusion arises from how we visualize motion. We imagine falling objects speeding up because something is pushing them faster and faster. In spacetime, however, the object's velocity changes because the notion of time itself is warped. The object follows a straight path, but our slicing of spacetime into space and time makes that path appear curved. Feynman stressed that this is not a trick of mathematics. It reflects how measurements are actually made. Observers at rest on Earth use clocks and rulers that are themselves affected by gravity. Their measurements encode the curvature of spacetime, and that curvature shows up as acceleration. This explains why gravity can be transformed away locally. In a freely falling frame, spacetime appears flat, and objects move as if gravity were absent. This is not an approximation. It is exact, provided the region considered is small enough that tidal effects can be ignored. Tidal effects, which arise from variations in gravitational influence across space, are the true signature of gravity. They cannot be eliminated by changing frames. Feynman liked this distinction because it clarifies what gravity really is. Gravity is not the feeling of weight or the falling of objects. It is the relative acceleration of near by free falling paths. If two objects fall freely and move toward or away from each other, that relative motion reveals spacetime curvature. This is gravity in its purest form. Everything else is a byproduct of our choice of frame. Feynman often warned that popular explanations focus on the wrong features. They emphasize the downward pull instead of the geometric relationships. As a result, people think gravity is about direction. In reality, gravity is about structure. This misunderstanding also affects how people think about energy and work. They imagine gravity doing work on falling objects, transferring energy to them. From the geometric perspective, energy conservation still holds, but its interpretation changes. Energy is not injected by gravity. It is redistributed through spacetime geometry and motion. Feynman did not deny the usefulness of older language. He understood that engineers and scientists routinely use gravitational forces in calculations. What he objected to was forgetting that this is a convenient approximation, not a fundamental explanation. When people insist on treating gravity as a force, they miss the elegance of free fall. They imagine the universe constantly pushing objects around. The geometric view reveals a universe that prefers simplicity. Objects move freely unless prevented from doing so. This idea has philosophical implications that Feynman rarely emphasized explicitly, but which underlie his thinking. It suggests that the universe is not full of hidden agents pulling strings. Instead, it operates through consistent relationships that require no intervention. The resistance to this idea is emotional as much as intellectual. We are uncomfortable with the thought that standing still is an active process. It contradicts our sense of effort and control. Falling feels dangerous and active. Standing feels safe and passive. Physics does not care about these feelings. Feynman believed that learning physics involves retraining intuition, not just memorizing facts. Gravity is one of the hardest cases because it is so deeply embedded in daily life. The more familiar a phenomenon is, the harder it is to see it clearly. This is why Feynman often returned to simple examples. Elevators, falling objects, astronauts, and scales are not chosen at random. They strip away assumptions and force us to confront what we really mean by motion and force. The idea that objects fall because they are following natural paths also explains why gravity cannot be shielded or blocked. There is nothing to block. Gravity is not something flowing through space. It is the shape of space and time themselves. Feynman found this deeply satisfying. It means the universe does not rely on invisible substances or mechanisms. It relies on structure. Once the structure is set, motion follows automatically. People sometimes ask whether this means gravity is unreal. Feynman would say the opposite. Gravity is more real than forces because it defines reality's structure. Forces act within spacetime. Gravity defines spacetime. This redefinition also clarifies why gravity is weak compared to other interactions. Its apparent weakness is not due to a small coupling constant, but to the fact that it is not an interaction in the same sense. Gravity influences everything by shaping the arena in which all interactions occur. Feynman often emphasized that this does not make gravity less important. It makes it more fundamental. Without gravity, there would be no consistent notion of motion at large scales. Orbits, stars, and galaxies depend on spacetime geometry. The mistake people make is assuming that if gravity were not pulling, objects would float away. In reality, objects would continue moving along their paths. It is gravity, understood as geometry, that allows stable structures to exist. In the end, the key insight is simple but devastating to intuition. Objects do not fall because they are forced to. They fall because they are free. The force we associate with gravity appears only when that freedom is denied. Feynman believed that once this is understood, gravity stops being mysterious and starts being logical. It no longer requires an invisible hand. It requires consistency in how space and time behave. This view does not eliminate wonder. It replaces a shallow wonder with a deeper one. The idea that freedom, not force, governs falling reveals a universe that is at once elegant and uncompromising. What everyone gets wrong about gravity in this context is thinking that falling is evidence of gravity's action. Falling is evidence of gravity's absence. The true mark of gravity is the pattern of free motion itself. Richard Feynman believed that one of the deepest reasons people misunderstand gravity has nothing to do with equations or intelligence. It has to do with the way the human mind is trained by everyday life. From the moment we are born, gravity is constant, silent, and unavoidable. We never experience its absence in ordinary conditions. As a result, our intuition about gravity is not built from comparison or contrast, but from habit. We mistake habit for truth. Human intuition evolved to help us survive, not to understand the structure of the universe. We learned to walk, lift, throw, and balance under Earth's gravity. Our muscles learned how hard to push. Our eyes learned how fast objects fall, and our brains learned what feels normal. Over time, these experiences formed a mental model of gravity that feels obvious and unquestionable. Feynman argued that this is precisely why gravity is so hard to understand correctly. When something feels obvious, we stop questioning it. Gravity feels obvious. Objects fall. Heavy things feel heavier. The ground feels solid beneath our feet. None of this invites curiosity. Yet this familiarity hides the fact that gravity behaves nothing like our intuition suggests. The universe does not care how things feel to us. It operates according to rules that were never designed to match human instincts. Feynman often pointed out that intuition works well only within the narrow range of conditions in which it evolved. At human speeds, time feels absolute. At human sizes, space feels flat. At human energies, gravity feels like a downward pull. Step outside this narrow range, and intuition begins to fail. Physics begins precisely where intuition breaks. One of the most damaging intuitive assumptions about gravity is the belief that rest is natural and motion requires explanation. When we stand still on the ground, it feels normal. When something moves or falls, it feels like something must be causing it. This leads us to think of gravity as an active agent and stillness as a default state. In reality, this intuition is backward. From the perspective of physics, uniform motion is just as natural as rest. What requires explanation is acceleration, not motion itself. Yet because we constantly experience the Earth pushing up on us, we mistake that forced state for natural rest. Gravity becomes the thing that causes motion, when in fact it is the thing that disappears in free motion. Feynman saw this as a profound lesson about perception. We feel weight because the ground resists us. We feel light when falling because resistance vanishes. Our senses tell us the opposite story of what is actually happening. The universe is not aligned with how it feels to be human. Another intuitive trap comes from direction. We instinctively think of gravity as pointing downward. Down feels like a fundamental direction, almost as real as north or south. But down is not a property of the universe. It is a local consequence of spacetime geometry and our position within it. Feynman liked to remind people that down changes depending on where you are. On the opposite side of the planet, down points in the opposite direction. Yet no one feels upside down. Each person's intuition insists they are standing upright. This alone should warn us that intuition is local, not universal. Gravity feels directional because our bodies use it as a reference. Balance, posture, and movement all depend on gravity's consistency. Our inner ear evolved to detect acceleration relative to gravity. As a result, gravity feels like a fixed background, not something to be questioned. Feynman emphasized that physics requires stepping outside this comfort. The laws of nature do not privilege human orientation. There is no universal up or down, no preferred direction in space. Gravity only appears directional because we live inside its effects. This becomes especially clear when considering motion in space. Astronauts experience no down, yet gravity is still present. Planets orbit stars without falling straight in, yet gravity governs their paths. The intuition that gravity means downward pulling collapses once we leave the surface of Earth. Feynman argued that intuition also misleads us about causes. When we see an object accelerate, we instinctively search for something pushing it. This works well for everyday forces like muscles or engines. Gravity violates this expectation. There is no visible pusher. Our minds invent one anyway. This invented pusher becomes an invisible force acting at a distance. Once this image takes hold, it becomes difficult to abandon. Even when told that gravity is geometry, many people secretly imagine curved space as something pushing objects around. They translate new ideas back into old intuitions. Feynman warned that this habit blocks understanding. Geometry does not push, it constrains. Motion follows from structure, not from force. This distinction is subtle, and intuition resists it because we rarely encounter structure determining motion without contact. Another way intuition misleads us is by encouraging false explanations. People often feel satisfied once they can picture something, even if the picture is wrong. A pulling force is easy to picture. Curved spacetime is not. As a result, many prefer a comforting illusion over an accurate abstraction. Feynman had little patience for this preference. He believed that understanding means accepting answers that may feel uncomfortable or incomplete. Nature does not care whether we can visualize it. Demanding visual comfort is a human weakness, not a scientific principle. He often pointed out that even in everyday physics, intuition fails. A spinning gyroscope behaves in ways no one expects. Electricity flows opposite to how people imagine it. Light behaves as both wave and particle. Gravity is not unique in defying intuition. It is simply the most familiar example. Familiarity creates a dangerous confidence. People feel they understand gravity because they live with it. They feel less confident about quantum mechanics because it is unfamiliar. In reality, both require abandoning everyday intuition. The difference is that gravity hides its strangeness behind routine experience. Feynman believed that education often reinforces this misunderstanding. Gravity is taught early, using simple formulas and everyday examples. Students learn how to calculate falling times and weights, but rarely learn what gravity actually is. The mathematical success of these formulas creates the illusion of conceptual clarity. Later, when students encounter Einstein's ideas, they feel betrayed. Gravity suddenly becomes complicated, abstract, and strange. They believe physicists changed the story. In truth, the story was always strange. The early simplicity was a useful approximation, not the full truth. Feynman emphasized that approximation is not deception. It becomes deception only when we forget that it is an approximation. Gravity as a force works well within limited conditions. Problems arise when we mistake it for reality itself. Intuition also encourages the belief that explanation must involve causes similar to human actions. We ask what causes gravity, expecting an answer like a push, a pull, or an exchange. When physics offers geometry instead, people feel unsatisfied. Geometry feels passive, impersonal, and abstract. Feynman argued that this dissatisfaction reveals more about us than about nature. The universe is not obligated to explain itself in terms of human actions. Explanation in physics means consistency, prediction, and coherence, not storytelling. He often compared gravity to rules in a game. The rules do not cause the game to happen. They define what can happen. Spacetime geometry defines what motions are possible. Objects move accordingly. Asking what causes the rules misses the point. This perspective challenges another intuitive belief, that deeper explanations must always be simpler in human terms. Sometimes deeper explanations are simpler mathematically, but harder conceptually. Gravity as geometry is simpler in structure, but harder to imagine. Feynman embraced this difficulty. He believed discomfort is a sign that learning is happening. When intuition fails, new understanding becomes possible. Everyday experience also misleads us about scale. Gravity feels strong because it dominates our lives. In reality, it is extraordinarily weak compared to other interactions. A small magnet can lift a piece of metal against the gravitational pull of the entire Earth. This fact surprises many people because it contradicts lived experience. The reason gravity feels strong is not because it is strong, but because it always adds up. All mass contributes, and there is no cancellation. Intuition does not naturally grasp accumulation over vast scales. It responds to immediate sensation. Feynman saw this as another example of intuition's limits. Our senses are not designed to detect cumulative effects over planetary distances. Physics extends perception beyond biology. Perhaps the most important intuitive mistake is the belief that understanding should feel natural. People assume that once something is understood, it should feel obvious. Feynman rejected this entirely. True understanding often feels strange because it contradicts deeply rooted assumptions. Gravity does not feel intuitive when understood correctly. Falling being force, free does not feel obvious. Time slowing in gravity does not feel obvious. Space influencing motion does not feel obvious. That discomfort is not a flaw. It is a sign that we are no longer confusing habit with truth. Feynman believed that learning physics means learning to distrust certain instincts, while trusting logical consistency and evidence instead. This is not easy. It requires humility and patience. He often said that the pleasure of understanding comes not from comfort, but from clarity. Clarity may feel unsettling at first, but it replaces confusion with coherence. Gravity becomes less mysterious not because it feels familiar, but because its behavior becomes predictable and consistent. What everyone gets wrong about gravity, in this deepest sense, is assuming that human intuition is a reliable guide to fundamental reality. Gravity exposes this assumption more clearly than almost any other phenomenon. It shows us that the universe operates according to principles that do not care how things feel. Feynman did not see this as discouraging. He saw it as liberating. Once we accept that intuition is limited, we are free to explore reality as it is, not as we expect it to be. Gravity stops being a comforting background and becomes a doorway into the true structure of the universe. In the end, gravity teaches us a lesson beyond physics. It teaches us that understanding requires letting go. Letting go of familiar pictures, letting go of sensory certainty, letting go of the demand that nature make sense on human terms. The universe is under no obligation to be intuitive. Gravity reminds us of this every moment of our lives, quietly, constantly, and without explanation. And it is only when we stop trusting that quiet familiarity that we begin to see gravity for what it truly is.